Hi everyone, my name is Miguel Martinez. I'm a graduate student in mechanical engineering, and today I'll be defending my master's thesis titled Primary and Secondary Resonances of Fringe Effect Electrostatically Actuated MEMS Cantilever Resonators. My advisor for this research is Dr. Dumitru Caruntu. Here's an outline of what I'll be discussing. I'll be going over some background, the importance of this research, what models and methods we use, and then I'll get to the results that we got. MEMS stands for Micro Electromechanical Systems. These are small-scale devices that can be used as sensors, actuators, or resonators. MEMS come in a variety of shapes. In this research, we focused on a cantilever, but there's also plates, membranes, or more complex shapes. The main advantages of MEMS include size, cost, and power consumption. MEMS are used in a wide range of applications. Recently, MEMS have become a very active area of research within the biomedical field. Such devices are known as biomems. An example of this includes dynamic biosensors, which detect and measure pathogens based on changes in resonant frequency. Electrostatic actuation of MEMS involves the attraction of two oppositely charged electrodes, which generates an electrostatic force between them. This force is due to the parallel plate capacitance of the system. Simplicity and accurate control of the device are some advantages of electrostatic actuation. Here you can see how a MEMS cantilever vibrates when an AC voltage is applied. When the electrostatic force overcomes the elastic restoring force of the beam, the cantilever becomes unstable and makes contact with the ground plate. This results in a short circuit within the system, potentially leading to failure. This behavior is known as pull-in, and it's considered one of the most important nonlinear phenomenon in MEMS. And this shows a MEMS cantilever reaching pull-in. This can either happen slowly or all of a sudden. The fringe effect involves the bending of electric field lines around the edges of the cantilever. Although the fringe effect has a much smaller contribution than the electrostatic force directly between the cantilever and the ground plate, it still plays a critical role in the cantilever's response. The objectives for this research are listed here. The goal is to investigate the nonlinear dynamics of a MEMS cantilever resonator driven by the fringe effect only. And this is done by having a hole in the ground plate directly below the cantilever. Both the frequency and voltage responses at parametric and primary resonances will be studied. We'll also look into the effect of dimensionless parameters and compare the different models used to predict the system's response. The importance of this work involves the ability of the cantilever to avoid pull-in and reach large amplitudes as it passes through the hole in the ground plate. This design offers a key advantage, especially for sensors or resonators, where avoiding pull-in is essential. And this shows a fringe-driven MEMS cantilever reaching large amplitudes. In this research, we used the method of multiple scales and the reduced order model to generate bifurcation diagrams. The method of multiple scales, or MMS, is an analytical perturbation method, which is used to solve a one-term reduced order model. One term meaning one mode of vibration. MMS is only accurate for small to intermediate amplitudes and weak nonlinearities. On the other hand, the reduced order model, or ROM, is a numerical method which uses numerical integration to predict time responses up to 5 modes of vibration. Unlike MMS, ROM is accurate for small and large amplitudes, as well as strong nonlinearities. This shows a schematic of the MEMS design being researched. Again, the cantilever is being driven by the fringe effect only due to the hole in the ground plate. The first model we used is the fringe effect model. This is a simple model that is based on Palmer's capacitance formula. The electrostatic force within the volume between the cantilever and the ground plate was assumed to be neglected, and only the fringe effect term was considered. Only fringe contributions acting on the top side of the cantilever are considered in this model. The second model we used is the capacitance model. This is an improved model based on an empirical capacitance formula. The electrostatic force was still assumed to be neglected. However, this model adds fringe contributions to the side walls of the cantilever, as shown here. And finally, we have the SolidWorks model, which is a realistic model based on numerical capacitance simulations performed on SolidWorks. This will end up being the most accurate of the three models, since it considers fringe contributions from all around the cantilever, including those that come from the underside of the ground plate and act on the bottom side of the cantilever. The dimensionless equations of motion are shown here for each model, as well as the boundary conditions. The equation of motion is basically Newton's second law. The first term is the force due to acceleration. This is the elastic force, and this is the force due to damping. On the right is the fringe effect force, which comes from the fringe field. The dimensionless variables and parameters are shown here. U is the dimensionless deflection. When U is 0.5, the cantilever is halfway between the initial gap distance. B star is the damping parameter, delta is the voltage parameter, and omega star is the AC frequency. Each model uses a different fringe effect parameter, F for the fringe model, F star for the capacitance model, and the SolidWorks model uses both F1 bar and F2 bar. This plot shows the results of the numerical simulations performed on SolidWorks. The fringe capacitance per unit length was calculated for different beam widths and gap distances. This expression was then proposed to fit the capacitance data points in the plot. Using MATLAB's fit nonlinear model function, the best fit constant coefficients were calculated and are shown here. The expression with these coefficients resulted in a coefficient of determination of nearly 0.92. This R-squared value ranges from 0 to 1 and determines how close to the fit the proposed expression is to the actual data points. The closer the R-squared value is to 1, the better the match. For parametric resonance, the frequency of the AC voltage, which is capital omega star, is near the natural frequency of the cantilever, which is lowercase omega. Epsilon is a small bookkeeping parameter, and sigma is the detuning frequency, which tells you how far away you are from the natural frequency. Since the voltage is squared, the frequency of actuation is near twice the natural frequency. For primary resonance, the AC frequency is near half the natural frequency, while the actuation frequency is near the natural frequency of the cantilever. For MMS, the force terms in each model are expanded in Taylor series up to the third degree, as shown here. This slide shows the uniform expansions, timescales, and time derivatives used for MMS. We have a fast timescale tau, which is dimensionless time, and we have a slow timescale epsilon tau. The time derivatives and expansions are substituted into each equation of motion. The problem is then separated based on the powers of the bookkeeping parameter. We have zero order and first order. The zero order problem is the same for each model, while the first order problem is different. The solution of the zero order problem, which is shown here, is then substituted into each first order problem. Next, secular terms are collected and their sum is set to zero. These are terms that contain e to the I omega t naught. The real and imaginary components are also separated and their sum set to zero. The steady state solutions are then found by setting A prime and gamma prime to zero, where A is the amplitude and gamma is the phase difference. Here you can see the equations for the frequency and amplitude for the fringe effect model at parametric and primary resonances. Since we're looking at the deflection at the tip of the cantilever, we defined U max as the amplitude A times the first mode shape of the cantilever evaluated at 1, which is at the free end of the cantilever. These are the equations for the capacitance model. And for the SolidWorks model, you can see how the equations get more complex with the capacitance and SolidWorks models. For the reduced order model, the solution of U, which is the dimensionless deflection, is given by the following equation, where n is the number of terms considered, U of tau are time-dependent coefficients, and phi of z are the mode shapes of the cantilever. Using the notation shown here, the equation is condensed into this form, where a and I and bn are notations for the rest of the equation. This equation is for n number of terms and is transformed into a system of 2n first-order differential equations, which are then solved through MATLAB to predict time responses, and also through Auto, which is a continuation and bifurcation software for ODEs. Here you can see the A and I and Bn equations for the fringe effect model. The H coefficients are also shown here. These coefficients involve integrating the cantilever mode shapes from 0 to 1. These are the A and I and Bn equations for the capacitance model and for the SolidWorks model. Since the SolidWorks model is the most complex, the equations do get pretty lengthy. The table shown here lists the different parameter values used for this research. This includes the cantilever length, which is 300 microns. The width is 20 microns. The thickness is 2 microns. And the initial gap distance is 8 microns. The values for each fringe effect parameter used for each model are also shown here. The first 5 dimensionless natural frequencies of the cantilever are listed in this table. This figure shows the frequency amplitude response for the SolidWorks model at parametric resonance. On the x-axis is the detuning frequency, which again tells you how far away you are from the natural frequency. And on the y-axis, we have U max, which is the dimensionless deflection at the tip of the cantilever. Just for reference, when U max is equal to 1, the cantilever tip is at the same level as the top of the ground plate. Only amplitudes up to 1.5 are shown, and this is because geometric nonlinearities, which become significant at larger amplitudes, were not considered in these models. The predictions made by each of the methods are shown here. This includes MMS with Taylor expansions up to the 3rd and 5th degree, as well as 2-term ROM auto and 2-term ROM time responses. Due to the complexity of the SolidWorks model, only a 2-term reduced order model was able to run for this specific model. The solid lines indicate stable solutions, while the dashed lines represent unstable solutions. Uh, the time responses shown have two different initial conditions. Uh, the initial condition is very important since it determines where the system will settle. You can think of unstable solutions as peaks and stable solutions as valleys, and the initial condition as what side of the peak you're on. The purpose of time responses is to verify the results from auto. Uh, for amplitudes less than 0.5, MMS and auto are in agreement. However, for larger amplitudes, the two methods diverge from one another. And this is to be expected since auto is accurate for large amplitudes and strong nonlinearities, while MMS is not. The MMS branches bend towards lower frequencies, which is called a softening effect, while the auto branches bend towards higher frequencies, which is known as a hardening effect. In this case, as the frequency is swept up, the amplitude stays at zero until reaching point A, which is the subcritical bifurcation point. Here, the system becomes unstable and undergoes a jump in amplitude towards the stable branch above, where it continues to increase in amplitude. On the other side, as the frequency is swept down from right to left, the amplitude is zero until reaching point B, which is the supercritical bifurcation point. Here, the amplitude increases quickly up until point D, which is a saddle node bifurcation point. This type of point forms when the curve reaches a vertical tangent line and transitions from stable to unstable, or vice versa. In this case, the system will jump in amplitude towards branch 3, then come back down until reaching point C, which is also a saddle node bifurcation point. From here, the amplitude will drop down back to zero. I should note that the region between points A and B is unstable and known as the resonant zone. On the left is a comparison between frequency responses of the three fringe models. The green is the SOLIDWORKS model, the blue the capacitance model, and the red is the fringe model. The dark lines indicate auto, while the light colored lines are MMS. The SOLIDWORKS model is the only one that uses two-term auto. The other two use five-term auto. By looking at this plot, we can see a rather noticeable trend, which is that as more fringe contributions are considered and the models become more refined, the response shifts towards lower frequencies and has a wider resonant zone. This means that as the frequency is swept up, a response is generated sooner with the SOLIDWORKS model than with either the fringe or capacitance models. And this is very important since by not considering fringe contributions from the underside of the ground plate, a response can be generated much earlier than expected, which can lead to inaccurate control of the system and possibly failure. The plot on the right shows the effect of having a hole in the ground plate. With a hole, which is the SOLIDWORKS model, the response shifts towards lower frequencies and has a wider resonance zone than the conventional response. This conventional response involves the electrostatic force and the electrostatic force plus the fringe effect. The SOLIDWORKS model is able to make predictions for amplitudes larger than 1, while the electrostatic models are limited to amplitudes below 1, since the cantilever can't go beyond the ground plate below. On the left, you can see an example of a time response that was used. And on the right is the effect of dimensionless damping on the SOLIDWORKS frequency response. In this case, increasing the voltage parameter causes the resonant zone to shrink, while the top two branches eventually coalesce to form a saddle node bifurcation point. Although the other two damping cases more than likely also form a saddle node bifurcation point, this happens above amplitudes of 1.5 which again cannot be verified. This shows the effect of the voltage parameter and beam width. On the left, increasing the voltage parameter causes the response to shift towards lower frequencies. The resonant zone also becomes wider since the subcritical bifurcation point shifts more than the supercritical bifurcation point. On the right is the effect of beam width. Although we usually look at the effect of the fringe parameter, the SOLIDWORKS model uses two different fringe parameters, which depend on constant coefficients. So instead of changing the values of the fringe parameters arbitrarily, we decided to vary the beam width instead. And this is very similar to the effect of fringe, since narrow beams, there's a larger fringe effect that has an influence on it. In this case, as the beam width goes from 20 microns to 10 microns, the response again shifts towards lower frequencies and has a wider resonance zone. We also see a more pronounced softening effect as the beam width decreases and a hardening effect. This figure shows the voltage amplitude response for the SOLIDWORKS model at parametric resonance. In the x-axis, we have the dimensionless voltage parameter delta versus Umax. Again, we see how MMS and auto match for small amplitudes, then slowly start to diverge above amplitudes of 0.5. The MMS branches bend towards lower voltages, while the auto branches bend towards higher voltages. To generate a proper voltage response, the detuning frequency chosen must be within the resonant zone of the corresponding frequency response. On the left is a comparison between voltage responses of the three fringe models. Since the resonant zone of the SOLIDWORKS frequency response does not overlap with the resonant zones of the fringe and capacitance models, two different detuning frequencies had to be used. Therefore, this is not a direct comparison. However, we can still compare the fringe and capacitance models. And what we see is that just by adding fringe contributions to the side walls of the cantilever, the response shifts dramatically towards lower voltages and the resonant zone shrinks. On the right is the effect of having a hole in the ground plate. Again, this is not a direct comparison since two different detuning frequencies were used. However, we see that the SOLIDWORKS branches behave much differently than the rest of the models. The SOLIDWORKS predicts a hardening behavior, while the rest of the models predict a softening behavior. This shows another time response that was used. On the right is the effect of dimensionless damping on the SOLIDWORKS voltage response. Increasing the damping parameter again causes the resonance zone to shrink, while the top two branches eventually start to converge at larger amplitudes. Here you can see the effect of the tuning frequency and beam width. Increasing the frequency and decreasing the beam width both cause the responses to shift towards lower voltages and the resonance zone to shrink. And in this figure, it shows the frequency amplitude response for the SOLIDWORKS model at primary resonance. MMS, auto, and time responses are shown. In this case, you basically get the same type of response whether you sweep up or down the frequency. The amplitude will increase initially, reach a maximum, then come back down. Although the two branches more than likely connect at their peak, this happens above amplitudes of 1.5. This shows a comparison between the SOLIDWORKS model and the other fringe models, and in this case, the SOLIDWORKS model with the other electrostatic models. In both cases, the SOLIDWORKS response is shifted towards lower frequencies. You can see how much larger amplitudes are reached with the SOLIDWORKS model than with the rest of the models. Uh, the SOLIDWORKS response is also the only one that remains stable throughout the range of frequencies. Here you can see another time response that was used for the frequency response. On the right is the effect of dimensionless damping on the SOLIDWORKS primary frequency response. In this case, increasing the damping parameter causes the response to reach smaller peak amplitudes, as shown here. Here you can see the effect of the voltage parameter on the left and the effect of beam width on the right. Increasing the voltage parameter and decreasing the beam width both lead to similar responses. And this is a key finding, since in case a certain parameter value is fixed and cannot be changed, other parameters can be varied instead to achieve a similar response. And finally, we have the primary voltage response for the SOLIDWORKS model. This one's pretty easy to follow. As the voltage parameter is swept up, the amplitude will increase throughout as predicted by Otto. The figures shown here compare the SOLIDWORKS model with the other Fringe and electrostatic models. Unlike before, this is a direct comparison since the same detuning frequency was used for each model. We see that the SOLIDWORKS response, it is the one that shifted the most towards lower voltages and the only one that remains stable throughout. Here you can see another time response. On the right, increased damping causes the voltage response to become more linear. And here we see how adjusting the frequency or beam width both lead to similar responses. In conclusion, we determined that the SOLIDWORKS model is the most accurate since it's based on numerical simulations and considers fringe contributions from the underside of the ground plate. The assumptions made in the fringe and capacitance models, in which the electrostatic force was simply neglected, it's not enough to accurately model the behavior of a fringe-driven MEMS cantilever. This lists some limitations and future work for this research. The main limitation involves the absence of experimental work, which is needed to verify the results that we got. Future work may include using different subharmonic or superharmonic resonances of different orders, as well as considering the geometric nonlinearities within the equations of motion, so we can see what happens above amplitudes of 1.5. And this lists some of the conference papers that we've published regarding this research. And here we are at the 2022 IDETC in St. Louis. And that concludes my presentation. Thank you.